Okay, so, well, it's a pleasure to be here, and I'm very honored to be invited to speak at this conference. Okay, so I'm going to be speaking about some joint work with Adam Jacob at UC Davis and Professor Yao. So, and the sort of topic of this talk is going to be about some relation between solving a certain nonlinear geometric PDE and algebraic geometry. So roughly, the talk is going to be in 3 parts or 5 parts. So the first part, I want to discuss the PDE, and in particular, I want to motivate it from mirror symmetry, because if I just wrote it down on the board, you might say, well, why do you care? So it's not something that I just made up. So in particular, I want to discuss this sort of SYZ transform of supersymmetric cycles, the relation to special Lagrangians, the deformed Hermitian Yang-Mills equation, and then maybe I'll say a few words about B fields. After that, I'll discuss a little bit the analytic aspects of this PDE, and then I'll say a few words about the algebraic aspects and the connections with various forms of algebra geometric stability, which appear in mirror symmetry. And at the end, I want to discuss a few related problems which give some evidence for a conjecture that I'm going to mention at some point. So, okay, so let me recall. So we've had many really nice talks at this conference about mirror symmetry, so this is going to be the only thing that I'm going to say really about mirror symmetry in any generality. So mirror symmetry was sort of discovered when physicists realized that certain pairs of Calabi-Yaos gave equivalent string compactifications of certain string theories. And in particular, they noticed that this sort of interesting duality related symplectic geometry on one Calabi-Yao to complex geometry on the other, and vice versa. So in some sense, mirror symmetry allows you to exchange the two. Kontsevich proposed that actually the right way to think about this was as an equivalence of triangulated categories. So on one side, we have the category of coherent sheaves, and on the other side, we have the Fukaya category. So this is a symplectic object, and the claim is that this should be equivalent to this complex object. So the mechanism for this equivalence was proposed by Strominger, Yao, and Zaslow, using what they called T-duality and a real Fourier-Mukai transform. So I want to say a little bit about the model case for this, which is semi-flat mirror symmetry. And it's really just a sort of local calculation, but it shows sort of why things work, or why we should maybe expect things to work. Okay, so for now, I'm going to have X2n be a Calabi-Yau manifold, complex structure J, holomorphic N0 form omega, and Kähler form omega. So the first thing I need to tell you is what the relevant symplectic objects are. So going back to Harvey and Lawson, we have an n-dimensional submanifold of this symplectic manifold is Lagrangian if it annihilates the symplectic form. And special Lagrangian if it's calibrated by this holomorphic N0 form. So in particular, up to rotating by some unit norm complex number, the imaginary part of this guy vanishes on L, which tells you that the real part has to be a volume form. Okay. So the proposal of SYZ was that in certain limits, so on the complex side and on the symplectic side, these two limits are different, but in these limits that we expect Calabi-Yaus to emit some sort of fibration. And the fibers of this fibration should be special Lagrangian tori. Then the way that we construct the dual, or the mirror manifold, is you just take the same fibration, but you replace all the torus fibers with the dual torus fibers. So the model for this, where you can sort of write things down, is semi-flat mirror symmetry, sort of an idealized case which serves as a local model for what would be happening here in this sort of best possible world. Okay, so this is how semi-flat mirror symmetry works. So suppose I'm given an affine manifold, maybe a torus. You can just imagine it's some fundamental domain in Rn. And a convex function on this set, B, which solves the real Magin-Pair equation. So then on the total spaces of the tangent bundle and the cotangent bundle, I have natural coordinates, right, just by taking the fiber coordinates in the usual way. And in particular, the tangent bundle has a natural holomorphic structure, right? You just take the complex structure which rotates the fiber coordinates or the base coordinates to the fiber coordinates and vice versa. And that makes these coordinates holomorphic. So we have these holomorphic coordinates on the tangent bundle. And the cotangent bundle, of course, has a natural symplectic structure. So we just take the usual symplectic structure on the cotangent bundle. And in particular, this guy makes the fibers Lagrangian manifolds. Okay. So we can now pull this convex function that we have on the base back to the total space and get a Calabi-Yau metric. So this is this guy. And we get also a dual Calabi-Yau metric on the cotangent bundle. And it's important to note that, right, naturally we should expect to have the inverse of the Hessian here. So if we imagine, okay, well, maybe I'll draw the picture in a second, but you should see lengths in the tangent bundle are inversely related to lengths in the cotangent bundle. So now so we want something compact, so the natural thing to do is take a quotient of this whole thing by some lattice. So we take some lattice in Rn and take lambda star to be the dual lattice. And then if you take the quotient of this picture, you get two compact manifolds, X and X check. And these guys are torus fibrations. So the fibers of the torus vibration on the left-hand side are exactly the dual tori to the fibers on the right-hand side, and vice versa. So this is the SYZ proposal in this case. And in this case, so explicitly, this Fourier-Mukai transform, it just takes a point. It takes a point on the fiber of this map and sends it to a U1 connection on the fiber of the mirror. So we have this picture. So we have here's our one Calabi-Yau that has torus fibers fibered over the base. And here's the mirror. Okay, so the way that I've written it, I guess the length of these fibers is 1 because they're supposed to be related by sort of inverses. But the idea is that you map a point on this torus to actually a U1 connection on the whole torus. So we get a flat connection on the torus on the other side. So these guys map to the same point. Okay, so this is the real Fourier-Mukai transform. And now you can sort of follow this through to compute how objects correspond under mirror symmetry. So the interesting objects are these supersymmetric cycles, which are the physically realistic states, which are, or in other words, D-branes, which are stable under decay. So on the Lagrangian side, the A model, the supersymmetric cycles are just special Lagrangians with flat unitary connections on the trivial bundle over L. So these are the objects we're interested in on the symplectic side. And now, in particular, one thing you could ask is, well, what if I have a special Lagrangian section? So in that case, I have some sort of section like this. So in particular, this section is special Lagrangian, and it meets every torus fiber in a point. So what that tells you under mirror symmetry, well, it sends each of these points to a flat connection on the torus on the other side of the correspondence. So that glues together to give you a line bundle, right? It gives you a line bundle, a holomorph or a complex line bundle over the mirror. And now you can ask, well, what does the geometric property of being Lagrangian correspond to? Well, you just do a local calculation, and what you see is that being Lagrangian is the same as this bundle being holomorphic, so it admits an integrable complex structure. what does it mean to be special Lagrangian? Well, now we get something slightly more demanding. You're special Lagrangian if and only if this bundle is both holomorphic and the curvature of the connection that you get on this line bundle over the whole mirror satisfies this nonlinear PDE, which is sort of a Monge pair type. So, right, so I'll say a little more about this in a second, but you see it has the same form as this special Lagrangian equation that I wrote down before, namely, I take the determinant, or the top wedge power of omega minus the curvature. I raise that to the nth power. That gives me an endomorphism valued n form. I rotate it by a unit length complex number, and I ask that the imaginary part of that guy is 0. So remember here, I haven't put an I in front of the curvature, so this curvature is really imaginary. Okay, so, and now you can ask vice versa, right? And it turns out to be the same. So a supersymmetric cycle on the B model on the complex side is just a bundle with a connection, holomorphic vector bundle or line bundle with a connection over a complex submanifold. And this connection is supposed to satisfy this equation. So the same sort of equation. So this was computed by Marino, Menasian, Moore, and Strominger, and this by Lung, Yao, and Zaslow. And this equation is called the deformed Hermitian Yang-Mills equation. So this is the equation I want to discuss today. And these, under mirror symmetry, these map back to special Lagrangians. So we have this correspondence between special Lagrangians on one side of mirror symmetry and bundles with connections solving this nonlinear PDE on the other side. Okay. All right, so the last, so I just want to mention, you can also do this computation to see what happens when you deform the complex structure on the symplectic side. And it turns out that that transforms to a sort of complexified symplectic form on the mirror. And if you want this thing to sort of map complex structures to forms, then you really need to take this form beta to be valued in H2R mod H2Z. So you don't account things modulo 2 pi. And for SYZ, if you want this vibration, so the 0 section of this vibration is supposed to be special Lagrangian, and that corresponds to this so-called B field, beta, being a closed 1-1 form which solves this sort of complex Monge pair type equation, so complexified Monge pair type equation. So again, sort of the same sort of equation, deformed Hermitian Yang-Mills kind of equation. Okay, so, right, so the question then is, well, suppose we have, so let's forget mirror symmetry now. We have some motivation to study a certain PDE. So we have some Kähler manifold, X omega, and let's fix another cohomology class in H11XR. And the question we're going to ask is, when can you solve this PDE? So when can we find a beta representing this cohomology class which solves this deformed Hermitian Yang-Mills equation? Okay, so let me just point out that this is equivalent to the deformed Hermitian Yang-Mills equation for the line bundle by just making this ansatz. Right. So this is the PDE we're interested in. Hopefully it's well motivated at this point. So let me say what we're doing. Well, we can take this Kähler form and we add I times beta, so this is a real 1-1 form. We take its nth power. That gives us a complex valued NN form. We divide by the volume form. That gives us a complex number, which it turns out always maps into C star. And the equation asks, well, we want this map, this number, this complex valued function, to always lie in a ray. So this is the condition that we're trying to impose, that this map maps into one fixed complex ray. So it won't have constant radius, but we just want it to have constant phase. So here, this angle, so let me point out, this angle theta hat is a priori only defined modulo 2 pi. So that's going to come up again shortly. Okay, so how do you work with this? Well, you have to write everything in local coordinates. So what does this equation look like in local coordinates? Well, in terms of this, so we can form this relative endomorphism where we raise, so we think of beta as a tensor, two tensor using the complex structure, and we raise an index using the metric. That gives us an endomorphism of T10, and we can take its eigenvalues. So the equation that we're interested in, so the angle of this complex number that I wrote down before, this guy, is just going to be the sum of the arctans of these eigenvalues. Right, so this is a perfectly well-behaved elliptic operator. And the deformed Hermitian Yang-Mills equation asks for this constant, or for this elliptic operator to be a constant. So the sum of the arctans of these eigenvalues should be a constant number theta hat. So this should be very reminiscent of the special Lagrangian equation for graphs in R2N. This is some complex version of that. Okay, but there's an important point here, which is that this constant, if we can solve this equation, this constant is valued in minus n pi over 2, n pi over 2, right? Because we're summing up n copies of arctan of lambda something. That gives us a number. So whatever this constant is, it's not just defined modulo 2 pi. It's actually defined in R. So this poses a slight problem. Well, it has two consequences. So the first consequence is that if there exists a solution to this equation, then this constant is unique, and it's defined, it's sort of determined modulo 2 pi by cohomology. So it's determined just by integrating this complex valued NN form over X, taking its argument, but that's only defined modulo 2 pi, and so that has to be equal to this constant, this target constant, modulo 2 pi. The second observation is that, well, this gives us a way to sort of unambiguously lift this number from just being defined mod 2 pi to actually being defined in R. So this topological quantity actually ends up having a perfectly good definition in R if we can solve this equation. So Adam and Yao proved that if you can solve the deformed Hermitian Yang-Mills equation, then this constant is unique. So it's not, you can't have two forms in the same class which have solve this equation with different values of the right-hand side. And it depends only on this homological data. Okay, so how do we determine this target angle? So I want to do a little bit of sort of mental gymnastics for a second, because I'm not going to tell you a good answer to this question until later in the talk, but here are four things you could keep in mind. So first of all, if this integral lands in C star, then we can determine the right-hand side of the equation actually at least modulo 2 pi. Right? We might not be able to determine it absolutely yet, but we can at least figure out what it is modulo 2 pi. On the other hand, if this integral is 0, then there's no hope of solving the equation. Because you see, if we could solve the equation, then this volume form, by taking the solution, this volume form would map into a fixed line, and by integrating over the manifold, of course, the average of this complex number would have to lie in this fixed line also. It couldn't sort of somehow add up to 0. And so we get a cohomological obstruction to solving the equation if this integrates to 0. And this really does happen. So I'll say more about that later. On the other hand, we don't actually need a solution to lift the angle. We just need something where the angle sort of doesn't oscillate too much. Then we can lift the angle. And if no such chi exists, then clearly we can't solve the equation, because that's saying that there is no 1-1 form that doesn't oscillate too much. But of course, we're trying to make this oscillation be 0. So, and the other thing I would note is that if this integral is 0, then you can't have a form which doesn't oscillate too much, because these things all map. The only way I could have something, so if every 1-1 form has average 0, that means they all have to oscillate more than pi, because you somehow have to have complex numbers on both sides of the origin in order for them to all add to 0. So this is just some simple observations. Okay, so let's assume we can lift the angle. And let's study the problem in the case when this target angle is quite large. So this turns out to be the best thing to do from the analytic standpoint. So I'll say a few more things about that later. But let's introduce the notion of a subsolution. So a subsolution, or C subsolution, is going to be a 1-1 form. Oh, that should be B. With the property that it maps into the right interval. And if I remove, so if I look at the sum of all of the arctans of the eigenvalues of this 1-1 form, and I remove one of them, I should get something that's bigger than my target angle minus 2 pi. Right? This is, of course, a necessary condition to be able to solve the equation. Because if I have the sum of the arctans of the lambda j's being theta hat, j equals 1 up to n, well, if I remove any one of these, I can't be removing more than pi over 2, because arctan is valued between minus pi over 2 and pi over 2. And if I put it on the other side, then I have to have an inequality. So this is a necessary condition. So then the theorem is that, well, if you have a subsolution, then you can prove a priori estimates for solutions of the deformed Hermitian Yang-Mills equation. So it's not so important what the statement of this theorem. The point is just that you can prove a priori estimates. So let me just say a couple words about how this is done. So there are sort of three estimates that you need to prove. You need to prove C0, C1, and C2. After that, you can use this sort of general theory of elliptic PDEs. So the C0 bound follows from the Alexandrov-Backelman-Pucci estimate. The C2 bound is really the hard one. So for the C2 bound, we have to apply the maximum principle to a pretty complicated quantity. But you do a sort of calculation, and by applying the maximum principle, what you deduce is that you get a sort of partial C2 estimate. So you get a C2 estimate which depends on a C1 estimate. So you're not done yet. All this says is that if the C2 bound blows up, then so does the C1 bound. But the key point is that this estimate is scale invariant. So you see if I rescale the coordinates on the left-hand side, well, I get two copies of the rescaling factor out because I'm taking 2 derivatives. On the right-hand side, I get 1 copy of the scaling factor out, but I get it squared because of this, because it's the gradient squared. So that's your friend. You can apply a blow-up argument to this and a Liouville theorem to deduce a C1 bound. Once you have the C1 bound, that gives you the C2 bound. And that proves the a priori estimates. And I would point out, so the reason that you really want to restrict to this large angle case is that if you look at these lower angle cases, then actually this elliptic operator sort of fails to have good properties. In particular, it has sort of even non-convex level sets, so it's not a priori clear whether you should expect to have any kind of estimates. Right, so let me not say any more about that. So the theorem that comes out of these a priori estimates is that if there exists a C subsolution in the class beta, then you can solve this deformed Hermitian Yang-Mills equation in the large angle case. Okay, so a few remarks about the equation. So you can think of so this existence of a subsolution is necessary and sufficient. Morally, the way to think about this is that the analytic assumption that there exists a subsolution in this class is the analog of the existence of a Kähler metric in a fixed cohomology class for Yao's solution of the Calabi conjecture. So somehow it's this sort of right condition to impose on a class if you want to try to solve the PDE. So the rest of this talk, I want to understand whether we can replace this analytic condition with some algebraic condition. So like in the case of Nakai-Moishazan or Demailly-Pound theorems, you would like to say that, well, in order to be a Kähler class, I really just need to check some intersection numbers. Right? This gives you some effective way of checking whether a class is a good class for solving this equation. Okay, so there are some questions that we need to address. So the first question is, can we compute this angle algebraically? So is there some way to figure out what this angle is which doesn't depend on you knowing somehow that you have one of these nice 1-1 forms? The second question is, are there algebraic obstructions to the existence of solutions? And is there some notion of stability which is implied by, or better yet, is equivalent to existence of solutions for this equation? Okay, so I want to try to address each of these questions to some degree. So let me discuss how to compute this angle algebraically. So I'm going to assume that this class is the first Chern class of a line bundle, and this is just to make the formulas a little more appealing, and in particular to draw some connections with some categorical notions of stability that are going to come up in a little bit. So, okay. So in this case, F is the curvature of a metric, H, some Hermitian metric on this line bundle, and we can rewrite this deformed Hermitian Yang-Mills quantity in this way. This is literally a tautology, so I'm not doing anything here. But in particular, we can look at this quantity where we integrate this guy over the manifold. And now how do we define the lifted angle? Well, we look at this path. So we scale the metric omega by t, right, z t omega, and we look at this path as it winds around in C, hopefully in C. And we just follow it as it moves, right? And we count its winding number. So maybe it goes like this. So here the winding number would be something like theta hat of L would be between pi and 3 pi over 2. So this is a kind of typical example. And this is the right way to define this angle algebraically. So it depends on knowing this whole path inside of C. So that's the usual thing you want to do if you want to lift the angle of a complex number from 0 to pi to r, right? You take some sort of winding angle. Okay, so so let's do some consistency checks. So for the trivial bundle, gamma of t has constant angle, right? Because I can take the metric with 0 curvature. So in that case, this thing is just 0, so you just get the top, or this part is just 1. So you just get the top dimensional component here, so it's just a straight line. It doesn't wind at all. And this is consistent with the fact that the trivial bundle has a trivial solution to the deformed Hermitian Yang-Mills equation given by taking this sort of constant metric. Okay, so when is this angle defined? Well, it's always defined in complex dimension 1, and so that's trivial. In complex dimension 2, it's always defined, but that turns out to be a consequence of the Hodge index theorem. In dimension 3, already you run into trouble, and the reason is that you can have paths which pass through the origin. So there are paths which do this, and this guy is bad. Because as soon as he passes through the origin, there's no obvious way to lift the angle. We can't keep track. Okay, and in fact, such examples already occur on the one-point blow-up of P3. So this sort of the simplest example where you have more than one cohomology class, you already run into trouble. So, okay, so if this guy turns out to be defined, and L has a solution of the deformed Hermitian Yang-Mills equation, then this definition computes the right thing. So this gives us an algebraic lift of the angle that we can compute just in terms of topology. And then this sort of, a hint for things to come later is that line bundles with this large angle condition are exactly the ones which end up, after this long path through C, end up in the restricted upper half plane. Okay, so I want to say one more thing, which is that in dimension 3 we know quite a bit more. So in dimension 3 we can prove a Chern number inequality. So in particular we can prove that if you have a line bundle over a Calabi-Yau or over some Kähler threefold with a solution of deformed Hermitian Yang-Mills in this large angle case, then actually this path never passes through the origin. And this follows from a Chern number inequality. So you solve the equation, and then you use the equation to prove a Chern number inequality like this. And the key thing here is that this Chern number inequality involves the third Chern class. So that's something which had sort of been important. People have been looking for Chern number inequalities like this, and it turns out that at least in the case of a line bundle in dimension 3, we can get this kind of Chern number inequality from the equation. So this implies that if you can solve the equation, then this lifted angle is always well-defined algebraically. So that's a good sign. So from now, I want to consider dimension 3, essentially because of this. But I should say that in general, we expect to have a similar kind of result involving all of the Chern numbers, all the way up to the nth Chern number. But it sort of gets computationally much more difficult. So. OK, so dimension 3. OK, so how do we produce cohomological obstructions to this equation? Well, there's a natural way to do that. You take this subsolution condition, which we know has to be satisfied, and we know is equivalent, actually, to the existence of a solution. And then we're roughly just going to integrate it over subvarieties. So if you think about, well, how do you get obstructions for a class being a Kähler class, you do the same thing. You say, well, if my class is a Kähler class, it has a positive form, I can integrate its powers over subvarieties, and that has to give me positive numbers. OK, so that's the sort of model. So we can do that, and this is the obstruction that we get. So suppose you have a line bundle in dimension 3. If there exists a solution to the deformed Hermitian Yang-Mills equation, then we have one of these subsolutions, and you can compute these angles. So notice here there's a v, a subscript v, and that's because I'm just integrating this kind of deformed Hermitian Yang-Mills quantity over v, so over a subvariety. And then I'm taking the winding angle of that guy. And the result is that if there's a solution, then you have to have this kind of inequality. So the angle on v has to be bigger than the angle on x minus the codimension of v times pi over 2. OK, so I want to write this in a more suggestive way. Right, so similar things hold in all dimensions. So the conjecture, right, so we said that if you have a subsolution, you get these inequalities. Well, in the Kähler case, we know, so if you were interested in producing Kähler forms, that you actually have a converse. So if you have these kind of intersection inequalities, you should expect to have a Kähler form. So the conjecture is that these inequalities are actually necessary and sufficient for solving the deformed Hermitian Yang-Mills equation. OK, so let me write this in a more appealing way, or a more suggestive way. So let's rewrite what this conjecture is. So a line bundle L admits a solution of the deformed Hermitian Yang-Mills equation with this large angle condition, if and only if the following two things are true. So first of all, this Chern number inequality has to hold. And that tells us, if this Chern number inequality holds, that tells us that this path that we get from looking at taking t from plus infinity to 1 never passes through the origin. And actually, we also know that this number has to lie in the upper half plane. And furthermore, for any irreducible analytic subvariety, we can look at this number. It also has to lie in the upper half plane, and it has to satisfy an inequality for the arguments, like this. So this is kind of like a slope inequality. This is the kind of thing that you see in the Donaldson-Uhlenbeck-Yau theorem. That's one way to think about it. Except notice here that we're looking at subvarieties here. So we have some sort of torsion sheaves appearing. OK, so in this formulation, when you write it out this way, everything sort of appears to be related to the stability of L in the sense of Bridgeland. So I'm not going to say what a Bridgeland stability condition is. It's some categorical version of stability. But the point is that the relation should be that this Chern number inequality, together with lying in the upper half space, should imply that L lies in the heart of some conjectural stability condition on the derived category with this central charge. And then the statement that we've made is that L tensor a skyscraper sheaf supported on V lies in the heart, and L is not destabilized by this surjection. So L surjecting onto L tensor the skyscraper sheaf. So I said should be here because I'm lying a little bit, which is that this definition of the central charge that we need to use for our stability condition turns out not to be the same as this Bridgeland type central charge. And the problem is that the Bridgeland central charge, well, our central charge is missing terms which depend on the Todd class. So maybe what you really want to do is throw in a factor of the Todd class here. And then probably you also want to consider things with B fields here. But anyways, that's somehow we start seeing these Bridgeland type stability conditions reflected in this PDE, even in the case of rank 1. Okay, so a remark for people in the audience who are familiar with this Bridgeland stability stuff is that I'm not claiming that these angles that we get out of the deformed Hermitian Yang-Mills equation define the slicing angle in a Bridgeland stability equation. In fact, the relation between these two is dependent on the dimension of the support. So just a technical detail. Okay, so let me do an example to sort of convince you that we can compute these kind of things. So consider the 1-point blow-up of P3. There's 2 line bundles up on this guy. We can pull back the hyperplane bundle from P3, and we can take the exceptional divisor of the blow-up. So that gives us 2 line bundles. So this guy is ample, so we'll take him to be the polarization omega. And we're going to consider the stability of these. I put an H there. That should be O1. Well, I guess it's fine. So anyways, AK, which is going to be the stability of this tensor power. Okay, so you can compute the angles of this guy. So you just expand this thing, you get some polynomials, and then you plot them on Mathematica and see what happens. And compute also, let's compute also the central charge on this subvariety E, right? So that's a perfectly good analytic subvariety that I could check stability on. Well, you get a picture like this. So here's A10. A10 takes this path through C, ends up here. This ZE is always on the real axis, right? Because you get this guy. And A1 takes a path which sort of stops earlier. So here are the sort of relevant angles from the deformed Hermitian Yang-Mills equation, right? They're valued in these ranges. And now if you look, well, the argument of Z of A10 is much, much larger than the argument of ZE of A10. So that guy is destabilized. So we can't have a solution to deformed Hermitian Yang-Mills on A10. But A1 doesn't have a problem because the argument of ZE is bigger than the argument of ZX. So that guy is not destabilized. So this is a sort of simple example where you see this kind of stuff coming up. So let me give you some evidence for this conjecture. Well, it'd be a relief to know that the conjecture is true in dimension 2. This is still not trivial, so it depends on Yao's solution of the Calabi conjecture and a theorem of Demailly-Pound, which gives you a numerical characterization of the Kähler cone. So you can check that these stability condition that I wrote down before exactly implies that the sort of relevant class lies in the Kähler cone. So the point is that in dimension 2, you can rewrite this equation as a Monge-Ampère equation, and then solving it is equivalent to the class being Kähler. So, okay. So another thing you can do is you could say, well, the equation's much too complicated, but let's do some sort of linearization. I mean, it's not a linearization, but let's look at sort of the highest order terms. So if we take this class B to be ample, and you rescale by a large parameter, and you take t to infinity, so now this class B is going to be much, much larger than this Kähler form, so we're going to call this the small radius limit. Then you get this kind of equation. And actually, this equation has appeared a lot in the literature before in relation to a lot of different things, so moment maps, sort of infinite dimensional moment maps. It arose in Donaldson's work from that perspective, and in Chen's work in the study of existence of constant scalar curvature metrics. So this is on Kähler manifolds. This guy is called the J equation if you ignore the T inverse term here. Okay, so motivated by K-stability for Fano manifolds, Lejmi and Shekihidi studied a notion of stability for this J equation, which is the sort of large or small radius limit of our equation, and they proposed the following conjecture. They said, there exists a solution to this PDE if and only if, for every proper irreducible subvariety of X, of some dimension, any dimension between 0 and n, you have this inequality for these intersection numbers. So again, a slope type inequality. Okay, so I should say that our conjecture reduces to this conjecture. So up to taking some tangents or arctangents, our conjecture is the same as this conjecture. So this conjecture is now proved, at least in the case of toric Kähler manifolds. This is joint work with Gabor Szekehidi, not to Laszlo, who we heard about earlier, the Szekehidi brothers. So this you can think of as some evidence for our conjecture, if you're being optimistic. Right? On the other hand, it seems quite possible that there could be sort of other obstructions coming from some Bridgeland stability condition, which is sort of yet to be constructed in general on Calabi-Yau threefolds, which could also provide some obstruction to the solvability of deformed Hermitian Yang-Mills, which we're sort of not seeing by this sort of somewhat simplistic construction of integrating this subsolution condition over subvarieties. So it may be the case that our conjecture is too optimistic, but there seems to be some good evidence for it. So I'll stop there. And happy birthday, JDG.
Okay, any questions for Tristan?
Mm-hmm. Yeah, so that's a very interesting question. So even the equation in the higher rank case is not, it's sort of, the supersymmetry requirement is extremely hard to work out. So I guess in this paper of Marino, Moore, Manazian, and Strominger, they had some proposal, which is our equation where now you just imagine F is the curvature of a higher rank bundle. But it becomes a lot more difficult to analyze. So for example, that equation is sort of not obviously elliptic, and it's not clear how to write it as a good elliptic equation. But we expect, at least from the algebra geometric standpoint, you can make many of the same sort of constructions. So it seems to have, if you imagine that it had the same structure, then it seems like it would fit into the same framework. Even for the case of a direct sum of line bundles, it's already quite interesting. So.
So can I ask you a question? So just to summarize, twisting by one, O, how does it change your angle?
Well, it depends on the bundle. So it's sort of
O of 1, for example.
Twisting by O of 1, twisting the actual line bundle by O of 1. Yeah, it depends. It's this process of computing the angle is sort of highly nonlinear. So twisting by O of 1, it may not change the angle, or it may change the angle quite a lot, depending on where you are in the.
I see. And then because this is very similar to Bridgeland. I mean, the third question will be, did you run this with Bridgeland or Emmanuel Macri? Because they have done this for projective threefolds. For example, the blow-up of P3 that you mentioned, I mean, there is this stability condition construction.
Right, so actually, yeah, so I gave this talk in Edinburgh last week, and Emmanuel Macri was there, and I gave this example just for him, because,
okay.
Yeah.
And the shifting, does it also depend, your angle, does it, I mean, if I shift the object in the draft category by 1 or -1, how does it?
Yeah, so it does the right thing. It swaps, it shifts by pi. Yeah.
So is there any other questions for Tristan, please?
What's the definition of the higher Chern numbers for a line?
Oh, they're just powers of C1. Yeah, it's just e to the C1 and then extract. Yeah, I wrote it like that because people who do Bridgeland stability like those, like CHs instead of just C1s all over the places. So, yeah, just to make it suggestive.
Questions?
I want to ask a probably fundamental question. So when we start besides Kähler manifold, so is it possible to find a B-model for which A-model is only symplectic and has almost complex structure?
Yeah, so I think, I'm not an expert in that, but I think Yao and Suchong Lau have a lot of work in this direction for non-Kähler mirror symmetry. Yep.
Other questions? If there is none, let's thank the speaker again. And also, let's thank the organizers of the conference once more, and all the speakers.